Hello and welcome to this manufacturing process technology part 1 module 39. We were talking about how you can express FC, the cutting force, in terms of the shear force and ultimate yield shear stress strength of the material that you are cutting. And in context of that, we wanted to do some optimization for the total amount of power requirement that would be used for cutting processes. So we basically tried to map Fc, the cutting force, in terms of the shear force Fs cos of lambda minus alpha divided by cos of phi plus lambda minus alpha in the last module, and we further expressed this Fs from an earlier equation as a function of the material properties and also the total cutting area by W T1 tau s sin divided by sin phi, where tau s is the ultimate shear yield strength of the material and W T1 by sin phi was the total interfacial area between the chip in the cutting zone and the workpiece from which it would otherwise get separated. So, if we substitute the value of Fs from equation let us say 11, which we had done earlier, all the way to equation 12, Fc comes out to be equal to W T1 tau s cos of lambda minus alpha divided by sin of phi cos of phi plus lambda minus alpha, and the power consumption which is otherwise taken as the force velocity product, that means the cutting force times the velocity, the feed velocity or cutting velocity. So, that is basically the power that is consumed in the separation of the chip. So, basically the power consumption during machining is given by W equal to Fc times of velocity v, that is the cutting force times the velocity of the cut, and this comes out to be equal to V W T1 tau s cos of lambda minus alpha times of 1 divided by sin phi cos of phi plus lambda minus alpha. So, as nature always tries to take the path of least resistance, during a cutting operation, phi would take a value such that the least amount of energy be consumed per unit time, consumed, or W is minimum, W being the total amount of work done in order to do the chipping process successfully, which is minimum. So, as V small w width of the cutting zone, uncut chip thickness T1 and alpha are fixed quantities for a certain machine, given machining operation, if we assume that tau s and lambda are also time invariant. So, this is something that we are just assuming, although in the real case the friction coefficient as well as the ultimate yield strength of the material in shear would typically vary as a function of temperature rise or temperature increase. So, we are not considering that here in this, and we are considering this to be time invariant property and as such related to the property of the material. Then you can say that W is only a function, that is the total amount of work done per unit time, or total amount of power that is consumed. W is only a function of phi. So, W actually is a function of phi. So, therefore, we can also say that this is equal to some constant here, which is related to all these different parameters V, W, T1, alpha. You have cos lambda minus alpha, so even lambda and Ts divided by the term sine of phi cos of phi plus lambda minus alpha, and we assume that minimum power would be consumed only corresponding to a certain orientation of phi. So, basically we have to minimize this number here, the total amount of power or work done per unit time with respect to phi, okay, and see at what phi values this power consumption would be minimum, or it would again, the angle would formulate in a way as if the cutting action is happening through the least path of resistance being offered to the tool surface, which is otherwise scraping through the material to remove it. So, W phi will be minimum when the denominator is maximum which can also be obtained by differentiating this with respect to phi and putting equal to 0. So, we have again cos phi, cos of phi plus lambda alpha minus of sin phi, sin of phi plus lambda minus alpha equal to 0, or cos of 2 phi plus lambda minus alpha equal to 0, which can only happen when 2 phi plus lambda minus alpha is pi by 2. Okay, and so this is the kind of condition. Also, obviously, lambda is, as you know, tan inverse of mu. We are assuming mu to be constant, invariant with time. So, that is the optimum machining criteria. And definitely the phi would take a value which would be dependent on this particular relationship corresponding to the minimum power consumption. Therefore, the equation two phi plus lambda minus alpha equals pi by 2 provides a way to determine the shear angle corresponding to a certain value of alpha and friction angle lambda. So, we have a sort of optimization criteria here. So, the value of Fc can be evaluated corresponding to this condition of 2 phi plus lambda minus alpha equal to pi by 2. So, the Fc was recorded as Wt1 tau s cos of lambda minus alpha divided by sine of phi cos of phi plus lambda minus alpha. So, if I put the value of phi plus lambda minus alpha from the relationship obtained earlier, it can be obtained as pi by 2 minus phi. 2 phi plus lambda minus alpha was pi by 2 by the relationship. So, I substitute this value here and try to see what happens to this equation. So, this becomes equal to W width of the cutting zone times thickness, uncut thickness, tau s shear stress cos of lambda minus alpha divided by sine of phi cos of pi by 2 minus phi. In other words, this can be represented as sine square phi, and sine square phi if I just substitute, if I just multiply numerator and denominator by 2, can also be written as 2 w t1 ts tau s cos of lambda minus alpha divided by 1 minus cos of 2 phi. Okay. So, cos of 2 phi obviously is nothing but, again if I look at this particular equation, can be pi by 2 minus lambda minus alpha brackets. Okay. So, we just substitute that again and try to see what happens or what form the equation would take. This is twice w t1 tau s cos lambda minus alpha divided by 1 minus of sin lambda minus alpha. Obviously, cos of pi by 2 minus lambda minus alpha would be sin of lambda minus alpha. So, this is ultimately the form which comes out from for the FC value on this particular optimum criteria corresponding to the value of phi that has been recorded using this power minimization criteria. And Merchant found out that this theory yields quite agreeable results when cutting synthetic plastics, but agrees poorly with results of machining metals. So, there was a small modification done by P.W. Bridgman, who realized that the shear stress, ultimate shear stress tau s, is not completely independent of the normal stress sigma, which would come into picture. In fact, what alternate theory he proposed was that can we relate the tau s to a basic tau s 0 value plus something proportional to the normal stress sigma that is coming at the shear plane, okay, where K1 is a constant and sigma is the normal stress acting on the shear plane. Let us just write this down. K1 is a constant and sigma is the normal stress acting on the shear plane. So, if I just substitute this value here for the tau s value, there will be some modifications which would happen to the overall equation. And if we look at what those modifications are, so we know that the if we just sort of consider what is the normal stress. So, the normal stress actually is nothing but the normal reaction which is given by the workpiece on the metal per unit area, okay. And actually it is the sine component of the angle phi of the normal force. And I will just like to redraw what I did before just to explain this concept here. Let us say this is the chipping formulation, or this is the chipping formation process which is happening, and this is the tool which is at certain rake angle alpha with respect to the perpendicular direction. And further, as I think I had illustrated earlier, we have a shear force acting in this direction Fs. There is a normal force which acts in a perpendicular direction, which is given by this vector right here. This is the normal force. So, this one is Fn, and this results in some kind of a resultant which is here, somewhere here, and we can say this is R. Just wanting to sort of repeat what we did in terms of the force diagrams. Also, we had two more forces, that is the frictional force to the chip as offered by the tool rake face, and the normal reaction which again was offered by the rake face, we call them Fnn. And obviously, there would be a third cutting and tangential force which would be offered by the workpiece onto the tool surface, because the tool is having a ploughing motion into the workpiece. Okay. So, having said that, obviously, the normal force on the shear plane due to which the normal stress would probably come up is because of this Fn value right here, and the area of the zone, I think, which we had done earlier was actually Wt1 by sin phi. So, that is also because the total amount of uncut chip thickness is T1, and the angle across which this thickness needs to be translated in order to get to the shear plane is phi. So, therefore, T1 by sin phi is what the length of this hypotenuse would be in this triangle, and W is the width of the cutting zone coming out of the paper or out of the board, okay, or going inside. So, this Wt1 by sin pi would be the total area of this particular face on which force Fn is acting. So, this is going to be the sigma value or the normal stress on the shear zone. And further, if I wanted to put this value in the suggested modification of Bridgman, the final shear stress would come out to be equal to two components. One is tau as 0 and another is some constant k1 times of this sigma value, which again is Fn sin phi divided by Wt1. So, there is actually a sin phi based variation in the total shear stress, which is because there is a component of the normal stress on the shear plane acting in order to define what is the ultimate shear yield stress of shear yield strength of the material at the zone of cut or zone of chip formation. So, we already know that we have a correlation between Fs and Fn, and so Fs by Fn was earlier recorded to be equal to tan of phi plus lambda minus alpha. If you remember the values that we talked about. So, the value here of if you look at Fn by Fs is really how to resolve it as components here in this particular figure. So, we have this angle equal to phi. If you may realize from earlier statements, this was the angle lambda, and the way we look at this angle was lambda minus alpha, which we had done in earlier calculations. This angle right here was actually alpha, and the angle taken here in this particular area was phi. So, obviously, the total amount of angle between the Ft and Fs in this right triangle would be phi plus lambda minus alpha. This right here is phi. So, phi plus lambda minus alpha. So, this is the total angle of the force triangle corresponding to the normal force in the shear plane and the shear force. Let me just separate this out here. This is Fs, this is Fn, and the angular relationship between these two. Therefore, the resultant of these two forces is at an angle of phi plus lambda minus alpha. So, obviously, Fn by Fs in this particular case becomes tan of phi plus lambda minus alpha. And having said that, if we wanted to now substitute the Fn value in terms of Fs in this equation, we would have the Fn equals to Fs tan of phi plus lambda minus alpha, and correspondingly tau s as tau s 0 plus k1 times of Fs tan of phi plus lambda minus alpha divided by Wt1 by sin of phi. Further, I can actually have now from this whole equation the value of tau s 0, which comes out to be Fs divided by Wt1 by sin phi times of 1 minus k1 tan of phi plus lambda minus alpha. The reason being that you have on one side tau s value, which you can write down simply from the earlier equation as Fs divided by Wt1 by sin phi. So, if you substitute this value in tau s, the tau s 0 value from this substitution comes out to be Fs by Wt1 by sin phi times of 1 minus k1 tan phi plus lambda minus alpha. Or in other words, Fs can be recorded as Wt1 tau s naught divided by this whole term right about here, which is sin of phi times of 1 minus k1 tan of phi plus lambda minus alpha. Or in other words, you can write this down as, again, if I just open this up as a sin by cos ratio, so I should be able to write it as Wt1 tau s naught times of cos of phi plus lambda minus alpha divided by sin of phi times of cos of phi plus lambda minus alpha minus k1 sin of phi plus lambda minus alpha. Okay. So having said that, we have now a relationship where we can again use the same logic, underlying logic of trying to find out the cutting force and trying to do the force velocity product and minimize the force velocity product to obtain a final solution which could be slightly different than the solution that was obtained earlier, which did not consider the assumption of the normal force. So this brings us to the end of this module 39, and in the next module we will do this force velocity product optimization and try to find out the new angle phi. Thank you.